All right. Tuesday is exam 3. That would be, what, the 7th? Yes. And the topics are everything up through the problems called Newton's laws. So that includes some things using Newton's third law. Every problem has Newton's second law in it, free body diagrams, and then all the old stuff that we've done too. Anybody have any problems you'd like me to go through? Practice problems? Okay. I don't have it in front of me. Anybody have copies of that? You what? Anybody else want to see number 4? Anybody want to see the crazy one at the end? Description, that one's sort of, I'll talk about that one because that was sort of, let me first talk about number 2. That's the one where you just have a box sitting on the floor. It says it has a mass of 100 kilograms. That's a lot. That doesn't really affect anything, but and it says that this block remains at rest when this 250 Newton force is applied. So what's the force vector that's required for this to stay at rest? So this force vector has x and y components that we don't know. And what force vector is required? So it stays at rest. And then for part B, it says now it's not at rest, it's moving with a constant velocity. But this is a Newton's second law question, and Newton's second law doesn't deal with velocities, it only deals with accelerations. What's the acceleration if you have a constant velocity? 0. And so parts A and B are exactly the same. That's just sort of this problem, that part of the problem is just set up so, to make you sort of recognize that. But all that matters for determining those forces is the acceleration, and the acceleration is 0 whether it's still or moving with a constant velocity. So here's how you would do this. This is really kind of more connected to the way I used to talk about this. I think that's why the solution, if you looked at it, looks a little confusing. I think probably eventually, maybe next time I teach this class, I'll get that one out of there and replace it with something else. But so I'm not going to ask a question very much like this on a test. It's not really that important to me anymore, but let me show you how I would think about this. So first I draw a free body diagram of the box. There's a weight force. 100 times 9.81 is 981. there is a 250 Newton force going this way. And then it says, okay, we're so just going to think about the force that's applied by the floor as an unknown vector. We don't know the x component or the y component. So I'm going to write that as a y component. I'll call it Fy. That's in the positive y direction. And then x component, Fx, that I'll just put in the positive x direction. And we'll just calculate both of those two components. So Newton's second law says the weight force, 0, negative 981, plus the applied 250 Newton force, positive 250, 0, plus, I'll just write this as a single vector with Fx as the x component and Fy as the y component. And those are equal to the mass times the acceleration. And in either one of the cases that this problem's dealing with, you have 0 acceleration, so these components are both 0. So the x equation says 250 plus Fx is equal to 0. So Fx is equal to 250. And the y equation says negative 981 plus Fy is equal to 0. So Fy is equal to positive 981. And all that together says that the force that's applied to the box by the floor has an x component of negative 250 and a y component of 981. And then it asks, okay, so this 981, this upward force of 981 newtons, that's the normal force we include in all these problems. And then it asks, what physically would apply that x component of the force? And in this case, that's the friction. It's static friction, which we haven't really done any problems with. But if I push, so say I'm pushing 250 newtons this way on this table, the reason it's not accelerating is that the static friction from the floor is pushing, counteracting it the other way until I push hard enough to get above the maximum static friction it can apply with the normal force it has, and then it'll accelerate. But basically, let's not spend a ton of time on that because I won't ask any questions like that. I think that's, yeah, so that's all. Anybody have any questions about that, though? Curious about anything? Yes. Right. That's right. Yes, exactly. So right, the normal, if there was no friction there, all you would have is that force Fy, and then that thing would have to be accelerating. Fx is the total friction force, which would be the coefficient times the normal force. But it wouldn't exactly be something we would calculate because, well, it could be if this thing was sliding. Then yeah, it would be the coefficient of friction times the normal force. Any other? So what other problems would you like me to go through? I think I will go through number 11. That one's really, really crazy. There won't be anything like that on the test, but I think it is sort of useful for just trying to work through these ideas, you know. Are there any before number 11 you'd like to see? Yes. Which one is that? Can you describe it? Oh, is that the same one? Is that number 11, but just the free body diagram? Okay. Yeah. Okay. Well, let's just do number 11, and then you have to do the free body diagram to do that. So in this one, you have a 25 kilogram box on the floor. And then on top of that box, there's a 10 kilogram box. And they're connected by a cable that goes over a pulley. And at this instant, it says the 10 kilogram box the top block is sliding to the left. So this one, that's the direction of motion for the top box. And if the 10 kilogram box slides an inch that way, which way does this one slide? What does this one do? Yeah, and it would have to be an inch. See that? If this cable stays the same length, however far you pull this one has to go the other way. And so we're going to use that for the relationship between the accelerations of those two objects. So the first thing I'm going to do is isolate the 10 kilogram box, use Newton's second law, see what we have. It turns out in this case that won't be enough, and we'll have to also isolate the second one and then solve it as a system of equations. Okay, so first free body diagram of the 10 kilogram. There's a weight of 10 times 9.81, so 98.1. And at the ground, there's a pushing contact. The 25 kilogram box is pushing up on this, on the 10 kilogram. So I'll call that N1. And then there's a friction force. At this instant, the 10 kilogram box is sliding to the left, so the friction force has to go this way. When I didn't say this, but it's in the problem that the coefficient of friction between the boxes is 0.1. And the coefficient of friction between the box and the floor is 0.2. So the friction that acts on the 10 kilogram box, is that the friction between the boxes or the friction between the box and the floor? Boxes, yep. So this would be 0.1 times that pushing contact between them, which is N1. And that's all the forces applied at the bottom. And then you get to the right side, and there's a cable force pulling this way. And we don't know what that is, so I'll call it T. And if you keep going around the boundary, those are the only forces. So that's the complete free body diagram. Any questions about the free body diagram? So then Newton's second law says 0, negative 98.1 plus 0 N1 plus 0.1 N1, 0, plus T0 is equal to the mass times the acceleration. And what do we know about the acceleration of this box? There's a 0 for one component. So yeah, the y component 0 because we know these things are only sliding along the x-axis. And so I'll just write this as A0. And we'll do what we do in every friction problem. We use the y equation to solve for the normal force. So negative 98.1 plus N1 is equal to 0, or N1 is equal to positive 98.1. By the way, if you ever get a negative answer for a normal force, something went wrong, because they always have to be pushing contact, so they always have to be positive if you draw them pointing toward the chosen body. And then the X equation says 0.1 times N1, which is 98.1, plus T is equal to 10A. So I'll rewrite this as T is equal to 10A minus 0.1 times 98.1 is 9.81. And now we've used both of these two equations. We can't go any farther. We can't solve for T and A because this is one equation for two variables. So we're just going to have to mark this and set it aside to use later. So now what I have to do is isolate the bottom box, the 25 kilogram box. Before I start doing that, we have to recognize this. These two forces together, the normal force and the friction force, if you add them up, that's the total force vector applied to the 10 kilogram box by the 25 kilogram box. Okay, that's a contact force. The friction is part of it, and the normal force is part of it. And so, okay, so I'm going to write this as force on the 10 by the 25. And if, when I write it this way, it sort of emphasizes the fact that when we want to figure out the force on the 25 by the 10, we can just use Newton's third law. So we can just take the opposite of this force vector and call that the force applied to the 25 by the 10. Any questions about that use of Newton's third law? So free body diagram of the 25. We have a downward force of 25 times 9.81. So that's 245.25. And then go around the boundary looking for contact forces. At the ground, there's a normal force. I'll call that N2. And there's a friction force. Which way is the 25 kilogram box sliding? I don't remember. So the 10 kilogram is sliding to the left. That means this one has to be sliding to the right. And so there's a friction force this way that has a magnitude of 0.2 times N2. And then keep going around counterclockwise, and you have the force applied by the cable. It's the same cable, just going over pulleys, so the magnitude is 10. And now you get up to the top, and this is where you have the force that's applied to the 25 by the 10. So what I'm going to do is just, these two together are the force vector applied to the 10 by the 25. I'm going to draw those same things here, just in the opposite directions, using the same variables. So I'm going to apply an N1 pointing down, and a 0.1 N1. Well, actually, now we know what that N1 is, too, so I can just put the numbers in. So I'm going to apply a force of 98.1 going down, and a force of 9.81 going to the, whatever that is, left.
Wouldn't it be going the opposite if the motion's going to the right?
Yes. Stupid. Okay, so that goes that way, right? And then there's the downward force of 98.1 and the force going to the left of 9.81. And the reason we're doing that is that, you know, this is from Newton's third law. We know those. And then keep going around. There's no other, nothing else from the outside world making contact with the boundary. So that's it for the free body diagram. So now put it in Newton's second law. And you get 0, negative 245.25 plus 0, positive N2 plus negative 0.2 N2, 0, plus positive T0 plus 0, negative 98.1 plus negative 9.81, 0. And all that is equal to the mass of what we're isolating now, 25 kilograms, times the acceleration vector. Okay, so what we figured out before is that if the top box slides, so think, since we already said that the top box has an acceleration of positive a0, okay, then think of the top box sliding an inch. I mean, forget about that we know the motion of the top box is to the left. Just think about the top box sliding an inch to the right in the positive x direction. Okay. Just because we have that one called positive a0. So if that slides an inch that way and that cable stays the same length, this one slides an inch that way. Okay, that if you really just push this one an inch to the right, that the cable would just, you know, fold up or whatever. But imagine that to get that to slide an inch to the right, you take this one and slide it an inch this way. Okay. So an inch to the left here, an inch to the right here is equivalent to an inch to the left for this one. So if I'm going to call the 10 kilogram acceleration positive a0, I'm going to call the acceleration of this one negative a0. That's what I'm trying to get at. So this acceleration is negative a0. And in any friction problem, we use the y equation, solve for the normal force, and then plug that into the x equation. So the y equation says negative 245.25 plus N2 minus 98.1 is equal to 0. So N2 is equal to, maybe I can do that, 243.35, 343. 343.35. And then plug that into the x equation, and you get negative 0.2 times 343.35 plus t minus 9.81 is equal to negative 25a. So that says negative 68.67 plus t minus 9.81 is equal to negative 25a. And so T is equal to, I think that's 78.48 minus 25A. And now we've gone as far with this pair of equations as we can, because our last useful equation has two variables in it, so we can't solve for those. So I'll just set this aside. And now what we have, if you look at the two red boxed equations, we have two equations for the same two variables, t and a, and we can solve them as a system. So here's our two equations for two variables. The first one says t is equal to 10a minus 9.81. And our second one says t is equal to 78.48 minus 25a. The right side of both of these equations is equal to t, so we can just set those two right sides equal to each other. So we get 10a minus 9.81 is equal to 78.48 minus 25a. And so you get 35a is equal to 88.29. And so then just divide by 35, and what do you get for a? 2.52 meters per second squared. And we're looking for the acceleration of a 10 kilogram box. And so the acceleration vector, the way we represented the acceleration of the 10 kilogram box was a0. So that's what we plugged this value into. And the acceleration vector of the 10 kilogram box is positive 2.520. Or in other words, 2.52 meters per second squared in the positive x direction, so this way. Okay, so one last thing. So is this system speeding up or slowing down? Well, slowing down because we said that the 10 kilogram box was moving, its velocity was to the left, or the acceleration is to the right, and so if the velocity and the acceleration are opposite, it's slowing down. Question? Okay. So yeah, there will be nothing like that on the test, but each one of those steps is sort of a useful thing, I think, for kind of practice, and especially, I guess I would say as you're getting ready for the test, focus on the other ones, and once you feel pretty good about it, see if you can work through that one. It'll sort of solidify some stuff. Yes, that's what I would say. Yeah, 2, don't really worry about that at all. 11 it's good practice, but it's just sort of beyond the scope of anything I'm going to ask. Any other homework questions you'd like to see? Okay, so let's do another sort of one that brings multiple things together. Was that supposed to be like, no, there's no more we want to see, we want to leave? Can't do that. There's too much physics out there. Okay, so say that we have a ramp that makes a 10-degree angle with the horizontal. And there's a block on the ramp. Let's say it has a mass of 1 kilogram. And then at the edge, there's a pulley. And the pulley connects the 1 kilogram to a 2 kilogram mass. And let's say that at the instant shown, the 1 kilogram mass is moving down the ramp. And the coefficient of kinetic friction between the 1 kilogram mass and the ramp is 0.2. And so we want to know what's the acceleration of the 1 kilogram mass. Okay, so mathematically, the way to go about this is just isolate one of these. Like, I'm going to isolate the 1 kilogram mass first. Go through Newton's second law, figure out what you can figure out, and then see if you have enough. And maybe you can do the problem, and if you can't, you just have to look for something else to isolate. So that's the way to think about it mathematically. But you can also tell intuitively that it's not going to be enough for us to just isolate the 1 kilogram mass. Why do you think that is? Like, looking at this, what tells you that isolating the 1 kilogram mass isn't going to be enough? Yes, exactly. I would just say, like, well, if we're not going to include this, obviously the acceleration of this is going to change depending on how heavy this one is. So somehow the equations have to get the information about how heavy that is. And so that's what we're going to see. We'll isolate this one. We'll get one equation, set it aside, isolate this one, get another equation, and then solve it as a system again. And in those kind of problems, we always use the relationship between the accelerations of the two. And so notice that if you move this one an inch that way, this one has to go down an inch. So that's what we're going to use. Okay, so I'll start with a free body diagram of the 1 kilogram. There's a weight force. That's 1 times 9.81, so 9.81 newtons. A normal force. And then this box is moving down the incline, so the friction force has to be up. So that's 0.2 times n. And then keep going around, and there's contact with the cable, so there's a cable tension T. And now we've accounted for all the contact with the boundary, so we're done. And now we have to put these into, yes? Yeah, that's fine. Yep, it doesn't matter where you put it, just put it somewhere so it's, as there's this little clutter, so it's easy to read, that's all. We're still assuming that everything is a particle, so really mathematically it's like everything is happening at the same point anyways. So to put it into Newton's second law, we have to express all these vectors as components, and that means that we need to choose a coordinate system. So for problems with sliding or rolling, we always choose a coordinate system with the y-axis pointing out of the incline. And that means in this case, the x-axis has to point this way. So in this tilted coordinate system, representing this force with a T is easy. That's just in the positive x direction. Representing the point 2n is easy. That's in the positive x direction. N is in the positive y direction, like it always is. A is just in the parallel to the x axis, like it always is in these. The one thing that's more complicated is representing 9.81. So let's figure out what that is. So I'm going to do that the way I always do. I think, let me see. No. I don't know. Okay, I'll just draw it. So first I'm going to just draw the horizontal and the vertical. Okay, that's not the coordinate system, that's just reference. So because we're going to use that, well, so why does the horizontal and the vertical matter? Because in these problems, the angle is always given relative to a horizontal. So we're going to at some point be using an angle between one of these two things in our coordinate axes. And now I'm going to draw in the coordinate system. So there's the positive x direction. There's the negative x. There's the positive y-axis. Negative y. And now we can read just directly off the picture that the relationship between the x-axis and the horizontal here is 10 degrees. So this is 10 degrees. Okay. And if that's 10 degrees, then the angle between these two has to be 10 degrees. And the angle between these two has to be 10 degrees. And this one, 10 degrees. And now I'm going to draw in the weight force. The reason I'm putting that in is like this whole system is just set up so that we can calculate the components of the weight force. I'll put the tail at the origin. And there's the vector we're trying to figure out. It has a magnitude of 9.81. And so we want to figure out the counterclockwise angle from the positive x-axis around to the force vector we're looking for. So from the green x to y, that's 90. And then 90. And then to this green would be 270. But we hit the vector first, so it would be 270, backtrack 10, so the angle is 260. So theta is 260. Yeah. Yeah, well, each pair of these, of the green axes is 90 degrees apart. So 90, 180, 270. We don't want to go all the way to the green one. We just want to go from the x-axis to the force vector that we're trying to find the components of. So you go 270 and then you've gone 10 degrees too far. So subtract 10 and you get 260. And then that force vector is equal to the magnitude of that force, 9.81, times cosine of 260, and then 9.81 times the sine of 260. Can someone calculate those? Negative 1.7, I'll just call it 1.70. Negative 9.66. Okay, so there are the components of the weight force vector. Before we go on, does it make sense that both of those components are negative? Yes, because in this tilted coordinate system, anything between these two is the third quadrant, and so both components have to be negative. So now Newton's second law says negative 1.70, negative 9.66, plus 0n, plus 0.2n, 0, plus T0 is equal to the mass, 1 kilogram, times the acceleration, and this thing is going to move parallel to the x-axis, so we'll just call that A0. And the y equation says negative 9.66 plus n is equal to 0, so n is equal to 9.66. Plug that into the x equation, and you get negative 1.70 plus 0.2 times 9.66 plus t is equal to a. And I'll just rearrange it a little. Let's see, 19.32. I think that's positive 0.23. So T is equal to negative 0.23 plus A, I think. Let's call it that. Okay, so now you can't do any more with that equation. Because you just have one equation, two variables, so you can't solve it. So we're just going to set that aside. We'll end up solving this as a system again. And now we go on to isolating the hanging mass. Any questions about that first step? Yeah. Mm-hmm. Yeah. We don't know what it is, but even if we did know that it was going to be in the negative x direction, we just write it as A0 because the sign will come out with the numbers. Okay, so you don't even have to think about that. But we do know that it's moving that way, but we don't know that the acceleration is going to be that way. Gravity is, the weight of this is going to try to pull it that way. The weight of this is going to try to pull it the other way. So, yeah. Yeah. Yeah, we're going to have to do that with this, and we're going to have to think about the coordinate system here. With the last example, we used the same coordinate system for both, but there's no reason you have to do that. You can think of them as sort of two separate problems, as long as you have a relationship between the variables. So when we isolate this one, we're going to go back to just our usual coordinate system with the y-axis up. Otherwise, you can imagine how messy it would be to, this force is going to be at some funny angle with this. The weight is going to be at a funny angle. We'd rather just deal with the normal coordinate system. Okay, so now free body diagram of the 2 kilogram. There's the weight force. That's 2 times 9.81. And then there's the cable force, and that's the same cable as the one pulling on the other one, so that's going to be T up. And then put that in Newton's second law. You get 0, negative 19.62 plus 0, positive T is equal to the mass times the acceleration. And now we have to think about how those accelerations are going to be related. So if the 1 kilogram mass moves in its positive x direction, what does this one do in its coordinate system? Yeah, it goes down, which is the negative y direction. So if we call the acceleration of this one a0, we have to call the acceleration of this one 0, negative a. So 0, negative a. The x equation doesn't give us anything. The y equation says negative 19.62 plus t is equal to negative 2a. And I'll rearrange that a little. T is equal to 19.62 minus 2a. And then set that aside, and there's our system of equations. The two boxed red equations. So you need to make sure that the variables in each one are the same variables. But yeah, we have two equations for the two variables t and a, so we should be able to solve that. So we have t is equal to negative 0.23 plus a, and t is equal to 19.62 minus 2a. So combine those and you get negative 0.23 plus a is equal to 19.62 minus 2a. So 3a is equal to 19.85. And so what do you get for a? 6.63? 6.1 meters per second squared. And we're looking for the acceleration vector of the sliding block. So substitute this back into its acceleration vector, and you get that the acceleration of the 1 kilogram thing is 6.610. So is it speeding up or slowing down? Yeah, it's slowing down. We said at the beginning that the block was sliding down the incline, so if the acceleration is up the incline, it's this way, then that system is slowing down, and if you let it run for a couple seconds, it'll come to a stop. Any other questions about that one?
Is this supposed to be a perpendicular?
No, that's A1. The acceleration of the 1 kilogram thing. Okay, let me give you one problem to work on. So let's say that we have an incline this way. with an angle of 20 degrees from the horizontal. And there are two carts in contact, a 2 kilogram cart and a 3 kilogram cart. And let's say there's a 30 Newton force pushing up the incline and a 10 Newton force pushing down the incline. What's the force vector on the 2 kilogram by the 3 kilogram? So how hard is the 3 kilogram cart pushing on the 2 kilogram? Okay, so in a problem like this, we don't know the acceleration yet. What's the first step? Yeah, isolate the whole thing. So treat the 2 and 3 together like a single object. Calculate the acceleration vector. And then, now that you know the acceleration of each part of the system, then isolate the individual ones. Okay, so see if you can figure out how to work through this. Talk to each other, ask me questions if you get stuck. And after you work on it for a while, I'll go through it. All right, so the first thing is isolate both of them together. There's a weight force. The total mass is 5. So this is 49.05. And then there's a pushing contact. I'm going to call that the normal, the total normal. Time to shut up now. And then there's the 10 newtons here and the 30 newtons here. Okay, so now we have to calculate the components of that weight force. Our coordinate system is like this. There's the positive x-axis, positive y-axis. From the picture, you can see this angle is 20 degrees. And that means this angle has to be 20, and this one, and this one. And the weight force is this. The magnitude is 49.05. So the angle from the positive x-axis to here is 270 plus another 20, so 290. So the weight force is 49.05 times cosine of 290, 49.05 times sine of 290. Can someone tell me what that is? $43? Oh, 46.09. Okay. And then Newton's second law says 10, 0 plus 0 in total plus 16.78 negative 46.09 plus negative 30, 0 is equal to 5 times the acceleration vector of A0. Since this problem doesn't have any friction in it, the y component doesn't give us anything. Nothing in the problem asked us for any normal forces, so I'll just use the x equation. And it says 10 plus 16.78 minus 30 is equal to 5a. So 26.78, so 3.22. What? Negative 0.644. I believe it. Sounds about right. Okay. And so the acceleration vector is equal to negative 0.6440 meters per second squared. And now we can isolate the individual carts. And in this one, it doesn't matter which one we isolate. We're looking for a force on the 2 kilogram. But we could just as easily calculate the force on the 3 by the 2 and then use Newton's third law. But I guess let's isolate the 2 kilogram, since that's the force we're looking for. So a free body diagram of the 2. There's a weight force of 19.62. There's a normal force, I'll call that N2. There's a 10 Newton force. And then there's the pushing force applied by the 3 kilogram cart. I'll call that R for reaction force. The weight, if we went through the thing of figuring out the angle again, the angle would still be 290, just the same as it was for everything. So the weight force is going to be 19.62 times cosine of 290, 19.62 times sine of 290. What do you get for that? 1. And then what for the y component? Okay, so Newton's second law says 10 0 plus 0 N2 plus negative R0 plus 6.71 negative 18.44 is equal to 2 times the acceleration, which is negative 0.6440. And then the x equation says 10 minus r plus 6.71 is equal to negative 1.288. So r is equal to 16.99, something like that. Yeah, that's what I meant. And so then plug that back into, this is the force vector we're talking about. So the force vector on the 2 by the 3 is equal to negative 17.980. Or that's in the negative x direction. So this way with a magnitude of 17.98. And then based on that, what would be the force vector on the 3 by the 2? It would be 17.98 just in the opposite direction down the ramp. Okay, have a good weekend.